In this video, I wanted to look at fitting the data to a charging capacitor in Excel using Solver. So I have here the data, time versus the voltage across the capacitor, which increases. So I'll make a quick plot, highlight the data, insert XY scatter. Okay. And this is not one of the forms that Excel fits to. It's not an exponential decay. It's not linear. It's not polynomial. You can get close with a polynomial, of course, but it's not a polynomial. So physically, it's not a polynomial. So you'd just be some crazy overfitting. So what is the form? The form, I'm going to I'm making some space for some parameters. The form has then is a charging capacitor. If it's charged, if there's a resistor and a capacitor in a circuit, and you open close a switch and start charging the capacitor in time, then the form has two parameters. And one I'm going to call the saturation voltage, the voltage sort of that you were applying, then is going to ultimately be the voltage of the capacitor. And I'm just going to start that off at 1. And then a time constant, which I'll just call capital T, and I'll start that off at 1. And that's sort of related to how long it takes. So how long does it take to saturate, and what does it saturate to? Those are the two parameters. And then the actual form is the saturation voltage times parentheses 1 minus the exponential, open parentheses, of minus the variable time divided by the time constant, close the exponential, close the 1 minus. Then I'm going to come back. There are ways to do this while you're typing, but I can never remember them. So I just usually come back. I'm going to put dollar signs in my parameters. So my variable, I want to vary. And so I don't put any dollar signs there, so that when I copy the formula down, it will change. The A5 will turn to A4 and give me different times, but the two parameters will stay fixed. I'm going to vary them, but they're not going to vary within the set of data. So for the set of data, they will have one value, which then I will manipulate. So parameter versus variable. I'm going to get into the corner, get my thin cross, copy that down. Okay, and now I'm going to make a plot of this form and my data. So I'm going to highlight all 3 columns, come down here and copy up. That's actually a little bit easier. And I don't have any words in column C here. So in C3, I don't have any words, so I should not highlight that. If I highlight that, it can confuse Excel. So either I should put something here, and then I can highlight it, or not highlight it when I'm making the graph. Okay. Insert, there we go. Make this. Okay, so here, the blue is my data, and the orange is my fit. So again, I said it saturates up to 1 at this stage, and it takes, at this time constant, is related to like how that's the amount of time to get to sort of 63% of this saturation voltage, and that I'm saying takes, in this case, 1 second. I'm going to do a quick layout number 9. I'm not interested in the linear fits, then it gives me sort of automatically. Let me change this time to, I don't know, 20 for a second. And I wanted to have an easy way to get there. I can get to that line and get rid of it. Okay, I wanted the axis labels in the title. I wanted all that. So this was time in seconds. This was voltage in volts. I'll say this is what charging capacitor, and let me highlight here, go to select the data, this data series. I'm going to say edit, give it a name. So this was the first one, so this is the data. And then the second one I'm editing, and I'm going to say that was the fit. Okay, but don't always like, well, that didn't work. Try one more time, select the data series, edit. This was the data. Okay, and this was the fit. Okay, okay, there it is, data and fit. And I don't always like legends, but there we go. If you want the legend, there it is. And I'm going to sort of make this a little bit. Now you can see the game. The 20 is actually pretty close to the value, and the 5 is a little bit low. But let me sort of make it bad. Okay, so you can just, by knowing what these parameters do and seeing what data is doing, get pretty close. This is going to be, I think, close to 6 and maybe 25 or something like that. You can get them pretty close. Just with eye, your brain is pretty good. Your eye and your brain are pretty good at this. But let's pretend otherwise. Let's get ourselves some criterion for doing this. So how would what's a computer, what's an algorithm to do this in case your brain isn't so good or you want to do some really fine-tuned thing. So a standard method for fitting is what we call least squared. We want to take the difference between the data and the fit, or the deviation, or sometimes you'll see the word residual, and then we want to square that. I'm going to call it the deviation is the difference, and I'm going to go one more and square it, so I don't have. So the deviation is the difference between B and C, and that could be positive or negative. Our guess may be low, our guess may be high, and so we square it, and then it's always positive. And some people will say, that's why I say square, to get them all to be positive. So it's an error whether it's too high or too low. But I want to sort of make an error either way, a positive error either way, and then add them all up. But some people will say it gives more, and this is also true, it gives more weight to any mistake, any point that has a mistake that is sort of really off. It gives more weight to it, so it sort of punishes you for any bigger mistakes. So for both reasons, square the deviation. So I'm going to square it, so it doesn't matter if it's B minus C or C minus B. I'm squaring that, and then I'm going to copy that down. Okay, so that is for each point a measure of the error for that point, but we want to sort of get a simpler thing that is taking care of all the points, and so I'm just going to sum all of these. And again, they're squared, so these are all positives, no negative signs in sight. And I'm going to just pick some cell in Excel. I'll pick it up here near the top. I'm just going to sum all of these deviations squared. Okay, so there is that, the sum of the squares of the deviations. And now the game would be, again, you could come back to doing it by eye, and you would see that if you choose something better, say 6 and 20, then not there 20, but here 20, this number should come down. This is the goal, is to make the and this is where the term least squares comes. We square the deviation, and we want to make that measure of the square deviations as small as possible. So that's the least. That's Okay. Let me undo whatever I was just. Okay. So here is the game. And again, I'm going to make it bad and then make it have Excel make it good for me. And this is where now, so you can just sort of do it by hand and change these values. And we saw that it could be very good. We have now a criterion that we can have the computer use this is something we want to be small. We want the error to be small. And we can't, there's no simple method. If the parameters V and T are linear, then there's a simple sort of formula, and you don't have to do sort of any guessing. But we saw here that the saturation parameter is linear, but the time constant is certainly not. And even if we put it, some number times A4, that would still, it's in an exponential, it would not be linear. So that's, if it were an exponential decay, if I were over here on my discharge sheet, then there is some mathematical trick to make it linear. So if it were an exponential decay, there's a game to play to make it linear in the parameters, and then there's an easy solution, and you don't have to play any kind of a guessing game. Right now what we're going to do is we're just going to involve the computer in our guessing game, and for that we're going to use what Excel calls solver. It's not something that's always in Excel. It's something you have to sort of bring into Excel. And so you're going to go to File, More on my screen, Options, and I want an add-in, and it's under the tool pack. And I have some of the tool pack, but I don't have the whole tool pack. So I'm going to highlight that and say go. And then there's this list, and I have the tool pack in there, but I don't have solver in there. So now I'm going to add in solver and say okay. And then you see sort of doesn't look like anything happened. But if you go over to the data item on the menu and come over here to analyze, there was my original data analysis that was there. And what I just did brought in solver for me. And that's what we want to do. We want to play with solver. And it does some iterative process. So we say, and I just happen to have this highlighted when I went to solver. So it's highlighting this E3, and that is the thing that I want worked on. That's my target, and I want something to happen to, and I want it to be minimized. I could also possibly say, since I know by design it was a positive quantity, I could say I want it to have a value of 0, but I'll go with minimum. And then what things am I willing to change for that to happen? My two fitting parameters, the saturation voltage and the time constant. Do I have any other constraints? Not at this time. You might say I want them both to be positive or something like that, but that's not much of a constraint. It doesn't need that constraint. But if you had important constraints, if this quantity could be minimized and violate some constraint in your problem, then you might have to come along and put in a said constraint. But I won't need that here. So I'm just going to hit solve. And now it's saying I had some success. I performed, down here it says 5 iterations, and the object did not move significantly after the 5, or from the 4th to the 5th. And so it's saying, I think I'm good. I like this. And it's saying, do I want? And you can see over here there they are, the 5.998 and the 26.69. And I could say, no, go back. I don't want to lose what I had. Or I can say, keep what you just did for me. So I'll say, okay, keep the solver solution. And so there are the values it picked. And here is now, you can't even see barely the blue. The orange fits the orange, the fit fits the data so well that it falls on top of it. And we could make it thinner. We could play games with the way we're presenting this image of make. Right now, they're both markers, and I might change the fit to a line and keep the data as markers to emphasize the difference between the mathematical function of the fit and the data, which is discrete points. But I'm not. So just at this point, I will end this here. And that's, again, what I wanted to do, sort of fit this data to some form. That form, the parameters in that form were nonlinear, so I did not have sort of set methods in just plain out of the box Excel to pick these parameters. But so we came up with a standard criterion of the least squares. So we found this residual or deviation, the difference between B and C, and squared that. So it's always positive, and got all those and summed them up. And then that was the thing, our criteria for picking values. Let's pick values that makes this small. And then because it was nonlinear, we needed a solver. So we brought solver in through the add-ins and just sort of said, here's my criterion. I want this sum of the deviation squared to be minimized. And the things I'm willing to change to do that are my two parameters, the saturation voltage and the time constant. And we see it's a pretty good fit. That's what I wanted to show you. Thanks for your attention.